In this sequel to the video on validation, we'll discuss k-fold cross-validation. Let's start with an example of two-fold cross-validation. In this case, we start by splitting the data into two folds of roughly equal size. Roughly 50% of the data is assigned to fold 1, and the other 50% to fold 2. The next step looks a lot like validation. We build or train a model using the data in fold 1, use it to make predictions for the cases in fold 2, and subsequently measure the resulting test mean absolute error, or MAE. The result, which we'll label as MAE2 to indicate that it's the testing error for the second fold, is 5.2. Now, if we stopped here, we'd just be doing validation, the potential drawbacks being that we're only using 50% of the data, and we might have gotten an unlucky split. So we won't stop here. Rather, we'll reverse the process. We'll build a model using the data in fold 2, use it to make predictions for the cases in fold 1, and subsequently measure the resulting test mean absolute error, labeled MAE1. This explains the cross part of cross-validation. The training and test sets cross roles in the two validation steps. Now we have two estimates of how accurately our model will predict the outcomes of new cases. Their average provides a more stable estimate. We call this average the two-fold cross-validation error, or CVMAE. Let's try the same thing, but using k equals 3 folds of roughly equal size. 34% of the data was assigned to fold 1, 33% to fold 2, and 33% to fold 3. From here, the cross-validation algorithm evolves in 3 main steps. First, we hold out fold 1 as the test set and combine folds 2 and 3 into a single training set. Thus, a combined 66% of the data will be used for training and 34% for testing. From here, the story is the same as before. We build a model using the combined training set, apply it to the test set, and calculate the corresponding prediction error, labeled MAE1 since it corresponds to the testing error of fold 1. In the second step, we hold out fold 2 as the test set, and we combine folds 1 and 3 into a training set. Using that training data, we build a model, apply it to fold 2, our test set, and calculate the resulting prediction error, labeled MAE2. In the third and final step, we hold out fold 3 as the test set, and we combine folds 1 and 2 into a training set. Using that training data, we build a model, apply it to fold 3, and calculate the resulting prediction error, MAE3. So at the end of this 3-fold cross-validation procedure, each fold has served as a test set and produces a unique measure of prediction error. Averaging these up provides the 3-fold cross-validation error associated with this model. The same concepts from 2- and 3-fold cross-validation extend to any number of folds k, where k can range from 2 to our sample size n. The general idea is this. In k-fold cross-validation, we split our full dataset into k folds of roughly equal size. For demonstration, here the data has been split into 10 folds. One at a time, we then hold out each fold as a test set. In the first iteration, we hold out fold 1 as the test set, build a model using the combined training data from folds 2 through 10, and then use this model to predict the outcomes of fold 1. We'll label the resulting prediction error by MAE1. In the second iteration, we hold out fold 2 as the test set, build a model using the training data comprised of the 9 other folds, and evaluate this model's performance on fold 2. We do the same thing for each of the remaining folds. In the end, each fold has served as a test set, thus has a corresponding prediction error, MAE. Averaging these up produces the 10-fold cross-validation error. In conclusion, k-fold cross-validation provides a more honest measure of prediction accuracy, thus helps prevent overfitting. It achieves this by avoiding the pitfalls of validation. First, recall that in validation, we only used, say, 80% of the data to train the model, thus lost some precious information. In contrast, so long as K is large enough, K-fold cross-validation allocates more data to training. On average, the result is a more accurate estimate of the model's predictive error. Second, we worried in validation that a bad random split could produce misleading measures of predictive error. In contrast, in K-fold cross-validation, we do the random splitting K times. Thus, even if one of the splits is bad, that is, includes data points that aren't representative of the whole, the average over all splits will give a more stable estimate of the true model prediction error. To wrap things up, let's address one big important question that we've ignored so far. In K-fold cross-validation, we must choose which K to use, where K can be any integer as small as 2 and as large as our sample size n. Thus, to implement K-fold cross-validation, we have to decide which K to use. Consider the two extremes. The smallest number of folds that we can utilize is 2. In this case, both folds include only 50% of the data points. That is, we're using only half of our available information to train the model. As such, our training models will likely perform worse than, hence overestimate the prediction error of our model that uses 100% of the available data. At the other extreme is K equals n fold cross-validation, also known as leave one out cross-validation, LOOCV. When we split the data into K equals n folds, each fold includes only one data point. Thus, when we set aside a fold for testing, we're leaving one out. Can you anticipate the drawbacks of this? Well, with n testing folds, LOOCV would require us to fit n training models. Even if we had a modest sample size of 1,000 data points, this would mean building 1,000 models. That can become very computationally expensive. There's also another more mathematically technical drawback to leave one out cross-validation. Since each testing fold includes only one data point, the training sets are largely the same. This correlation among the training sets makes the ultimate corresponding estimate of prediction error less reliable. If you're curious about these mathematical properties, I encourage you to take mathematical statistics. In practice, K equals 10 and K equals 7 are common choices for K-fold cross-validation. They've been shown to hit the sweet spot between the extremes of the computationally expensive K equals n, or leave one out cross-validation, and the biased extreme of K equals 2.